are present here. The embedded systems is advanced, recent trend developing systems, and the unit 1 is embedded architecture. We have the topics in this unit is embedded computers, characteristics of embedded computing application, challenges in embedded system design and process. We have requirements, specification, architecture design, designing hardware and software components, and system integration. So the first topic is embedded computers. Computers have been embedded into applications since the earliest days of computing. Example, worldwide. A computer designed at MIT in the late 1940s and early 1950s. It supports real-time operation. It has a mechanism for controlling an aircraft simulator. This is extremely large physically when compared to today's computers. Example, contained over 4,000 vacuum tubes. Computers were proposed to control chemical process in the late 1940s. So the figure is given, you can refer this. A processor is a single chip CPU. The first microprocessor, the Intel 404, was designed for an embedded application. For example, calculator. The calculator is not a general purpose computer. It provides basic arithmetic functions. Integrated circuit designs are expensive and time-consuming process. The ability to reuse the hardware design by changing the software was a key breakthrough. The microprocessors are classified based on the word size. At start with an 8-bit microcontroller is designed for low-cost purpose. The application includes onboard memory and input-output devices. A 16-bit microcontroller is often used for applications that require either longer word length or off-chip input-output memory. The 32-bit RISC processor offers very high performance for computation incentives application. The microprocessor types are given here. For example, micro oven has one microprocessor to control oven operation. Under the advanced thermostat systems, change the temperature level at various times during the day. In modern camera has powerful features that can be added under microprocessor control. Digital television uses embedded processor. Under the embedded computers, this is the architecture shown in the figure. Any device that includes a programmable computer but is not itself a general purpose computer. For example, cell phone, printer, automobile engine, brakes, dish, etc. Airplane, engine, flight controls, navigation, communication, digital television, household applications. The application example are simple control, front panel of micro oven, etc. Canon EOS 3 has 3 microprocessor. It is a 32-bit RISC CPU runs, autofocus and 8 control system. Under digital TV, programmable CPUs, hardwired logic for video, audio, decode or etc. are available. So this is a BMW 850i brake and stability control system. Of course, it is also based on the embedded system. That it has sensors, brake, hydraulic pump. It's shown in the figure. Actually, what is the difference between embedded computer and general purpose computer? In embedded system, it has a microcontroller based system. It is for specific purpose. Power consumption is less. Not end user programmable, runs a few applications often, known at design time. In general purpose computer, it is a microprocessor based system. It is for general purpose and power consumption is high, end user programmable. This is the basic difference between embedded computer and general purpose computer. The characteristics of embedded computing applications are: the first one is complex algorithm. The operation performed by microprocessor may be very complex. For example, the microprocessor that controls an automobile engine must perform filtering functions to optimize the performance of the car while minimizing pollution and fuel utilization. The next one is user interface. Microprocessors are frequently used to control complex user interfaces that may include multiple menus and many options. For example, GPS Global Position System. The next one is real time. Many embedded computing systems have to perform in real time. If the data is not ready by a certain deadline, the system breaks. Missing deadlines in printers can result in scrambled pages. And next one is multi-rate. Several real-time activities run at the same time simultaneously. Control some operations that run at slow rates and others that run at high rates. For example, multimedia applications, the audio and video portions of a stream should be synchronized. If failed, entire presentation is spoiled. Manufacturing cost. The total cost of building the system is very important. The manufacturing cost is determined by factors such as type of microprocessor used, the amount of memory required, the types of input-output device. The power and energy. The power consumption directly affects the cost of the hardware. The energy consumption affects battery life, heat consumption in desktop. So the next topic is challenges in embedded computing system design. So what are the challenges to design the embedded system design? First of all, how much hardware do we need? We need to know about that. Apart from the type of microprocessor used, care should be taken to select the amount of memory, the peripheral devices, etc. Both performance deadlines and manufacturing cost constraints should be met. Too little hardware system fails to meet its deadlines. Too much hardware, it becomes too expensive. So the next one is, how do we meet deadlines? Of course, the brute force way of meeting a deadline is to speed up the hardware so that the program runs faster. It makes the system more expensive. Increasing the CPU clock rate may not make enough difference to execution time since the program speed may be limited to the memory system. The next challenge is, how do we minimize power consumption? In battery powered application, power consumption is extremely important. In non-battery application, excessive power consumption can increase heat dissipation. One way to make a digital system consume less power is to make it run more slowly, but slowing down the system can obviously lead to. How do we design for upgradability? The hardware platform may be used over several product generations or for several different versions of a product in the same generation with few or no changes. Next is, does it really work? Reliability is always important when selling products. Customers rightly expect the products they buy will work. Reliability is especially important in some applications such as safety critical systems. The next one is complex testing. Exercising an embedded system is generally more difficult than typing in some data. Limited observability and controllability. Embedded computing systems usually don't come with keyboards and screens. This makes it more difficult to see what is going on and to affect the system's operation. Restricted development environments. The development environment for embedded systems are often much more limited than those available for PCs and workstations. The next one is the embedded system design process. The design methodology is important for three reasons. The first one is allows to keep a screen code on a design, for example, optimizing performance. Second one is it allows us to develop computer-aided design tools. The third one is a design methodology makes it much easier for members of your design team to communicate. The figure shows that the steps in embedded system design. So we have top to bottom and bottom to design. So the first one is top to down design. It has started with the requirements, specification, architecture, components and system integration. So under the bottom up design, we start with the system integration, components, architecture, specification and goes to requirements. The major goal designs as manufacturing cost, performance both overall speed and deadlines and power consumption. So these are the important steps in embedded system design. So embedded system design is very important emerging trends and today technology.